Hi, I'm Professor Goins. In this video, I'm going to look at finding the inverse of a function. Not all functions have inverses, of course, which we described in another video. But for the examples today, we're going to assume that all these functions do have an inverse. Okay. All right. Remember that the idea of an inverse function is that the function expression for an inverse is the inverse operation for the original function. For example, if I say that f of x is x plus 5, then the function operation here is to add 5 to an input. What's the opposite of adding 5? Of course, subtracting 5. Therefore, the inverse function is x minus 5. Another example, if I give you, let's say, g of x is x divided by 7, then the function expression here takes the input and divides by 7. The inverse of dividing by 7 will be multiplying by 7. Therefore, the inverse function is 7x. Now, what's unique about these examples right here is that the function expression has a single operation. In particular, look at these ones down here, which we'll work through here in a few minutes. This has two operations. So I've got a subtraction, I'm adding 1, taking a cube root, multiplying by 5. So I've got multiple operations going on. And we can't simply write down what the inverse is without going through some algebra. And even after you guys get good at this, and you can just write the answer down, you are still working the algebra in your head. Okay, so an important property of inverse functions is that let's look at this one right here. When I add 5 and then I subtract 5, I do those operations consecutively. The plus 5, the minus 5 cancels. If I do the operation of dividing by 7 and multiplying by 7 consecutively, then those two operations would cancel. So that's what's listed with this property right here. Remember, composition means I'm taking consecutive operations. So I perform this operation followed by performing this operation. And that's, again, captured by the concept of a function composition. So that means when I take the composition of a function with its inverse, they cancel. And I do that in either order. So I can either add 5, then subtract 5, or subtract 5, then add 5. It doesn't matter the order. Okay, well, I'm going to use this important property right here, the first one I have listed, and let's look at this function here, f of x and f inverse. So if I use the functions up above, I know that x is equal to f composed with f inverse. And I know that f composed with f inverse means this is f evaluated at the function f inverse. So now I'm using f inverse as the input for the function f. And what the function f does with the input is it adds 5 to it. So that means I've got x is equal to f inverse plus 5. Then look what happens if I think of that as an equation and solve for f inverse. I would subtract 5 to the other side, and I would get x minus 5 is equal to the inverse function, which is what we had guessed up above, right? That's what we had listed up above as the inverse function. So here's a verification for it. But what this shows me is this is then going to generate the method for how we can find inverse functions for an arbitrary function. Okay, so functions that are significantly messier, this would be very helpful for. In particular, what we did is let's go through here the procedure list up here, and then let's kind of compare it with the work we did down there. The first step you're going to do is replace f of x with y. So like in this equation right here, I would take this f of x and replace it with a y. Then I'm going to interchange x's and y's. So that means that this, which is y, this is x. I'm going to replace this will become a y, and this will become an x. And then once I do that, I'm going to solve the equation for y. Well, that's exactly what I did down here is I solved this equation for f inverse. Okay? And then once I do that, once I isolate y, that will be my inverse function. So once again, I'm going to, f of x gets replaced with a y. I interchange x and y, solve for y. Then once I get that y by itself, that is my inverse function. So here's the three examples that I want to work through. I've got a linear function, I've got a radical function, and a rational function. So a little bit different algebra with each one of those, but it's the same concept as far as swapping the x's and y's and then solving for y. Let me clean up this side of the board, and then I'll work through those three. Starting with the function f of x is 4x plus 3. What I'm going to do is I'm going to start by writing y is equal to 4x plus 3. And then this says to interchange x and y. So that means I'm going to get x is equal to 4y plus 3. Then this says to solve that resulting equation for y. Okay, so to solve this for y, I'll subtract 3 over. Then finally, I'll divide by 4. This then would be my inverse function. Okay. Swap x, y, solve for y. Okay. Now let's look at the radical function. First, I replaced f of x with y. Now I'll interchange x and y. So I've got x is equal to 5 cube root 1 minus y. And then I'll solve this resulting equation for y. All right, so then I'll divide both sides by 5, giving me x over 5 is the cube root of 1 minus y. Now I have to undo the cube root, so I'll take the cube of both sides. That would give me x over 5 to the third is equal to 1 minus y. And then what I'll do is I'll add y to both sides. Let me see if I can just kind of squeeze it in up here. So I'll add y to both sides. And then I'll subtract this term over to the other side. So that would give me 1 minus x over 5. Oh, sorry, parentheses in the wrong spot there. So that's x over 5 to the third. Okay, so I added y over to here, and then I subtracted x over 5 to the third over to the right-hand side. And that would give me y is 1 minus x over 5 to the third. And this is my inverse function. Before I do the next example, let's highlight this step right here. And also this one. Remember the property that I listed at the beginning where I said x was equal to, or I said f composed with f inverse of x is equal to x. So that's exactly what these steps say. Okay, notice this expression here is equal to x. This expression here is equal to x, just like this composition is here. If I look at 4y plus 3, this is the composition of the original function, and y plays the role of the inverse. So this right here is f composed with f inverse. Same thing down here. This is x is equal to, and if you look at the 5, the cube root of 1 minus something, that's the original function, and this right here is the inverse. So this right here is the composition of the function with its inverse. So it has that same format as the property that I listed originally. All right, let's go through, let me clean this part of this whiteboard up here, and then we'll go through part C. Part C. Okay, first step, same as the other ones. So I'll write down the original function with the f of x replaced with y. Then I'll interchange x and y, giving me x is equal to 4y plus 1 over 3y minus 2. My goal is to solve for y, so what I have to do is I have to get this out of the denominator. Okay, so I'm going to clear the denominator by multiplying both sides by 3y minus 2. That will then get distributed to both sides. When I multiply it to the left-hand side, I'll get x times 3y minus 2. When I distribute it to the right-hand side, the 3y minus 2 and this 3y minus 2 would cancel, leaving 4y plus 1. Okay, so now I've got y's out of the denominator, but I still have y's on both sides. So I have to get y by itself, meaning I'll have to group the y terms together. The way I'll do that is I'll take this x and I'll distribute it through the parentheses. That will allow me to maneuver terms. So 3xy minus 2x is equal to 4y plus 1. So again, need a little more space. This term has a y, this term has a y, therefore I want them on the same side. What I'll do is I'll take this 4y and I'll subtract it over to the left. And then this term right here, this minus 2x, that since that does not have a y, I want to add that to the other side. So again, the 3xy, that term will stay. This 4y, I'll subtract it from both sides, so it'll cancel on the right, and then I'll get a minus 4y on the left. Minus 2x does not have an x, or I'm sorry, does not have a y, therefore I'll add that to both sides, giving me a 2x over here, and we already have the plus 1. All right, so we're closer. I've got everything that has a y on the same side, everything that does not have a y on the other side. Now the way y is attached to both of those terms is through multiplication, which means we can factor it out. That will give me y times the product, or the two terms, 3x minus 1 is equal to 2x plus 1. 3x minus 4, sorry about that. 3x minus 4. Then what I'll do is I'll divide by what's in the parentheses. That would give me y is equal to 2x plus 1 over 3x minus 4. And again, there's my inverse function. Now what you can do is check the properties with each one of these three examples, A, B, and C, and take the composition of the original function with the inverse function and make sure that they simplify to get just an x. Okay? If that happens, then you know that you've got the right answer. So that's a nice check. It's also a good practice with composition.